So we have attendees trickling in. We are broadcasting to the general attendance, and it's up on Hoover.
Okay, great. So let's give it another minute or two.
Sure.
And of course, right now, the lawnmowers start in my house.
If the lawnmowers are in your house, you should probably rethink your house structure. If they're in the house.
Oh, no. We live in the woods, you know. Can you hear them, or is it just?
No.
Okay, well then we're good. All right, so folks are coming in. We see some 60 participants. We give it another minute before we get started. So folks, everyone find a seat. You have a good view on the podium on our next keynote. All right. Good morning, everyone. Good morning, good afternoon, good evening. Welcome back to our keynote sessions. This is the third keynote for this UbiComp and ISWC conference, and it's my great pleasure to introduce you to Phil Cohen. He will talk about the past, the present, and the future about dialogue research, and his talk is called Back to the Future of Dialogue Research. Wanted to give a bit of an introduction here. A key component in human-to-human interaction is speech, obviously, and more specifically, spoken dialogues. We rarely give monologues to each other. We typically interact in dialogues where we have like this back and forth, the dyadic interaction in speech. It allows us to respond to the interaction, to our interaction partner in a situated and somewhat adaptive manner. So in a way, dialogue makes what interaction makes, what makes interaction human. So here in this form of ubiquitous computing researchers has been a dream of many of us, of this whole field, basically to transfer this naturalistic way of interacting with each other into computing. And in fact, intuitive interaction, if you go back to the original vision papers in UbiComp, is essentially at the core of this UbiComp vision, right? And that defines our community. So spoken language dialogue has been around for a while. It has come a long way, and as a bit of an anecdote, when I did my master's and my PhD degrees, I worked a little bit in speech recognition, and so we basically also always defined from a speech recognition perspective coming like bottom up. So we started at a signal and made our way in the level of abstraction and understanding all the way to some level, and then we had other colleagues in the groups who were working on dialogues, who in a way came top down. And the fun fact is we actually never met. Right, so there was always this gap between the low-level speech recognition folks and the higher-level speech interpretation and dialogue folks. But things are very different now. So I think in these days, it is fair to say that speech recognition, can almost be considered as being a solved problem. There's tremendous progress. We can use speech recognition, automated speech recognition in many real-world applications on devices now. natural language processing has become huge in the past few years. And with the combination of both that leads to dialogues, to language-based understanding, there's commercial applications like Siri, like Alexa, et cetera, et cetera. They are being widely used. So one could argue that by means of the users being able to naturally interact with these kind of services, we kind of got very close to this mission accomplished goal of having this equivalent of natural interaction through speech. Or have we? So that's basically the setting for Phil Cohen's keynote over here. He will elaborate more on where are we right now in dialogue research and what's the future of dialogue research. And he will argue that future conversational systems that can engage in multi-party collaborative dialogues will require a more fundamental approach than existing technology, right? So there's more to come. And as such, his keynote will provide us with a critical analysis of what current natural language-based conversation systems actually can do and what remains to be done. I'm very excited about this talk and I look forward to that. Just a little bit about our speaker. Phil is an expert in the fields of human-computer dialogue, multimodal interaction, and multi-agent systems. His accomplishments include co-developing foundational theories of intention, collaboration, and speech acts, co-developing and deploying multimodal systems, and conceiving and leading the project SRI at SRI International that developed the open agent architecture, which we now casually call Siri. Phil just told us that he has very recently, today, congratulations, started as chief scientist at OpenStream. He also holds an adjunct professorship at Monash University in Australia, where he directs the Laboratory for Dialogue Research. He has been chief scientist, AI, and senior vice president for advanced technology at VoiceBox Technologies. He was a founder and CEO of Dapix Incorporated and program director of Natural Program AI Center at SRI International. He's also been very active academic with appointments, for example, at Oregon Health and Science University. He's published more than 150 refereed papers. It's widely cited with more than 18,000 citations, received 7 patents, and distinguished awards such as the inaugural Influential Paper Award from the International Foundation for Autonomous Agents and Multi-Agent Systems. So it's a great pleasure to have Phil here. The strong technical and application focus of the UbiComp community is, I believe, a very great setting for this talk. It's very timely. I very much look forward. And Phil, hand over to you. The floor is yours. Thank you.
Thank you for that great introduction and stage setting. So I'm going to speak quickly because we have a lot to cover. So yes, there has been amazing progress in speech recognition over the past decade, and there are many reasons for that. Both there was a huge amount of science that went into it, data collection, and also hardware, and recently, starting 2012, deep neural networks, although it had gone on long before that. But realize that the problem is relatively, quote, easy. What you're trying to do is recover the words. And it's made hard by the fact that there are so many words, there's so many voices, there's so many pronunciations, prosody, acoustic environments, and actually speech recognition doesn't work very well if you're in a cocktail party like multi-person conversational situation. But assuming that it works very well and you have the words, okay, so why doesn't this system understand me? Why can't we have a conversation? I'll direct you to this link from a couple of years ago about Alexa and Siri. But what makes it hard? Well, paraphrases, many ways to say something. Ambiguity, the words mean something different. Ungrammaticality, people don't speak good. What is a meaning after all? And then of course things change in context and I have to figure out what the pronouns refer to. Or prosodic changes. Boy, that's the best meal I ever ate versus that's the best meal I ever ate. Okay, they mean something entirely different. And finally, pragmatics. How are words used? When I ask you, do you have $1? Sometimes I might be asking you for $1, that's a request, and sometimes it might simply be a question, because if you don't have $1, I'm going to give it to you. So I'm going to argue that the central core of what's in dialogue involves people's plans and intentions. And without that, the systems can't really hold a conversation. Oh, but you say, but we have these chatbots. And I suggest there's less here than meets the eye. Essentially, chatbots are a way to try to avoid the problems of dialogue. And you train a system on a large corpus of stimulus response pairs, and it finds the most common response to the stimulus that it's given. So far, you've seen a lot of commercial applications of this, and some of them are successful to the degree you define success, but mostly they're failures. And you don't have very many transactional dialogue systems. And now, why is that? Well, I suggest that they're emulating this animal. They're parrots. Now, a parrot can imitate just about anything. I had a blue-fronted Amazon parrot like this, and this parrot could imitate a coffee grinder. It could imitate the beeps of a telephone, beep, 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 beep. And it could imitate half of a phone conversation. Yeah, okay. And if you turned out the light and lit a candle, the parrot would sing happy birthday. So you have the illusion that this creature is engaging in your conversation, but the parrot doesn't know what a birthday is, right? It doesn't know whose birthday it is. It's simply a great neural network. But I submit to you, the parrot is actually smarter than a neural network. The parrot has intentions. Well, how do I know the parrot has intentions? Well, I'd come home after a long day. I'd have my briefcase in hand. I'd walk past the parrot, and the parrot would say, hello. I'd continue past the parrot, not engage with it, and the parrot would go, hello. So it was trying again to achieve a goal that it had, which was to engage with me. That's a hallmark of intention, and I'll get back to that in the future. So what do these systems do? Well, here's an example of one. Bonjour. And the system says, how would you describe the term bot to your grandma? And you respond, my grandma is dead. And the system says, all right, thank you for your feedback. So these systems are, they don't understand a thing. Okay? No clue about what you're saying. So let's go back to the beginning of dialogue systems. Danny Bobrow and Terry Winograd's system in the 1970s, and Barbara Gross's system also in the 1970s. These were what I call frame-based or task-oriented dialogue systems. And that's basically what people are trying to build right now. They have a very limited goal. The system is intended to perform actions, like buy movie tickets, reserve restaurants, or all kinds of things that you might see on Alexa, for example. So the systems is intended we're building these systems to determine which action you're trying to get it to perform, and to prompt the user for the values of the parameters, the slots so-called, in the action frame. So the natural language processing you see is trying to figure out the action or intent classification, and by intent they mean the action you're trying to perform, and I'll suggest why that's too simplistic. And the slot filling, trying to fill in what are the arguments. So for example, the system might prompt you for slot values if you're trying to reserve a restaurant, the date and time you want to eat and the number of people. And you're supposed to, as the user, supply an atomic value, Monday at 7 p.m. And then the systems are built by trying to learn the optimal slot filling dialogue policies from data. And the data is generated typically by a user simulator, since they don't have as many, enough dialogues that are annotated. And typically you're going to see academic research competitions whose goal is to produce bold-faced numbers. But there are very few deployed systems. Now you might ask, why is that the case? Well, here's one example. People tend not to just provide values, they often provide constraints. So if you say, book me a table at Guillaume for Friday, and the system says, what time do you want to eat? A perfectly reasonable response is after 7, not before 7, between 7 and 8, or the earliest time available. Notice I didn't provide an actual slot value. I provided a constraint on the slot value. Or the user could say, what's the earliest time available? System says 6, user says too early, system says how about 7, the user says okay. So this is a mixed initiative interaction in which the parties collaboratively fill the slot. The user never actually fills the slot, the system does, and the user confirms it. So you want systems that know how to do this. And the current systems don't. These are deep learned, reinforcement learned systems, using one or the other or both of them. The machine learning for the slot filling will typically merge the natural language understanding and the dialogue data into one big melange, into a soup, and hope that that's going to cope with the dialogue variability. But there are huge amounts of data required, as you might imagine, in a dialogue. And these things tend to exhibit relatively poor performance when put up in real dialogue scenarios rather than in the artificially constructed ones. But to my mind, what's missing here is you need to learn to talk all over again for every domain, because I'm putting the natural language and the dialogue data together. So ultimately, we need to rethink, I submit, where's the variability? Is it in the natural language parsing? Is it in the speech recognition, or is it in dialogue manager? And it may be the case that different techniques are appropriate for each of them. So for example, speech recognition, natural language processing, well, deep learning might be the most appropriate technique. But dialogue management, I'm going to suggest you might want to do some plan-based reasoning. So I'm going to consider a collaborative dialogue. In fact, you could have multi-party collaborative dialogues. And the goal here is to build a plan-based dialogue manager. So speech recognition and other modalities will come in and be fused here at semantic parsing and multimodal fusion. And the output of that is going to be a meaning representation, which we'll call a logical form, and you'll see why. And then rather than do the kind of dialogue processing that I showed you earlier, what we're going to do is figure out what was the user trying to do, what was the user's plan, figure out what's wrong with that plan, if anything, and plan a response and execute that response, out of which comes another logical representation, which then leads to multimodal generation, text-to-speech, graphics, avatars, robots, etc. So there'll be lots of data sources that we need to keep track of, the system's beliefs and goals, the user's beliefs and goals, etc. And they'll be dispatching off to the back end, might be a mapping system, might be Yelp, something like that. All right, so you notice I broke up the process, and semantic parsing is the front end, and then there's dialogue management. So let's look at semantic parsing. This is one of the oldest problems in natural language processing, going back at least to Bill Woods in 1972, and Terry Winogrand about the same time. And in the beginning, people tried to do this via parsing, and they still do. We can discuss offline why that's the case. Nowadays, this is done with neural networks if you have enough data. So I'm going to give you some examples from a system we built at VoiceBox going back a few years. So imagine you say, where's the closest Korean restaurant? So the output is, we're going to call it a logical form here, and then we'll show you different kinds of logical forms. But basically, it's a meaning representation, which is an action. The action is to show the star refers to the topic. The topic is an amenity, which is a restaurant whose cuisine is Korean, which is nearest to here. And that's just syntactic sugar for an SQL query to a database. So current semantic parsers can build these things provided you give it the right data. But annotating huge quantities of data, which all the big companies have, is a non-starter. So how do you go out building these systems? That's why you don't have these systems, generally speaking, is because the annotation of the data to do the training is too hard. Well, what we did is we did it backwards. We start with what the system can do. We started with the APIs, and then we worked our way back. So if you build a deep learning sequence-to-sequence system for these kinds of models, sequence one, the first sequence is a sequence of words, and the second sequence is going to be the sequence of characters in this logical form. So now I need to know, how do I create pairs of these things in order to train it? So we're going to work backwards from the logical forms to the words. But before I show you how we did it, let me show you what we were able to do. Turn your volume up, by the way.
Take me to that Italian restaurant nearest to 4th Avenue and Virginia Street.
Here are the directions from current location to Assaggia Ristorante.
Now, my friend Mike wants Japanese food near the iconic Space Needle. Now, not knowing the city, I'd like to park nearby. Find the closest parking to the Japanese restaurant nearest to the Space Needle.
Here's the information on Mercer Street Garage.
Now, I'd like to meet Mike for coffee tomorrow morning, and we're staying in Bellevue. Find coffee that's not a Starbucks near Weston Bellevue.
I found the following cafe, coffee and tea house not including Starbucks near Weston Bellevue.
Take me to Top Pot Donuts and send the address to Mike.
I found the following, send it to Mike.
Okay, so Mike's now getting information on where to meet me for breakfast. Now, I'm searching for dinner reservations near the Westin Bellevue. We want to eat well, but not too expensively. So, which of the 3 best restaurants within walking distance of Westin Bellevue is the cheapest?
Here's the information on Facing East.
Okay, that's enough. So the way we built that system is you start with the logical forms, the meaning representations, and you generate a grammar of these logical forms such that you could generate lots of them. And then you paraphrase each of those logical forms into an utterance, which may or may not be fluent natural language. In particular, you could say, show restaurant where restaurant has Korean cuisine and the restaurant is nearest to here. Nobody would actually say that, but you could understand it. And then you give it to a crowd of people and you say, now paraphrase that for me. Show the nearest Korean restaurant, find the closest restaurant that serves Korean food. And that can generate thousands and thousands, hundreds of thousands of examples. It all depends on how much money you have and how well your crowd performs. And there are techniques for filtering out spam. And then, you have 50,000, 100,000 paired examples of utterances and their meaning representations now, which we've generated from what the system can handle. This is referred to as the overnight approach from a paper of Percy Liang's, and Wang is the first author from Stanford. So this avoids the problem of having to annotate. We're generating from the annotations. Now, if you can see this is examples of what that semantic parser was able to do as compared to, this was a few years ago, might have improved since then, Siri, Google Assistant, Hound, and Alexa. So if you take a specific example, find the nearest open pharmacy and take me there. Most of them can't do that. Alexa actually could. Where's the shoe store nearest to 3rd Avenue and Mercer Street? None of them could do that. In fact, offline, if you try find hamburgers in Seattle but not McDonald's, you'll find that Siri will give you only McDonald's. Okay? And that's because they're not parsing this stuff. So, we were getting, of course, I set it up. Of all these examples, we got these right. But you're seeing from Siri and Alexa, et cetera, anywhere from 38 to 30 to 64% accurate. But, you tell the folks at Apple, they say, oh, yeah, we know we can't do that. But only 15% of our utterances, they told me, are complex. Well, of course, 15% of a big number is a big number. Now, you're talking about billions. But, people learn that they can't do this. So they, that's why they're not getting these kinds of utterances. And if you try it, this kind of stuff with Alexa, you'll find something similar. So to summarize, semantic parsing, neural net semantic parsing can be quickly deployed to new languages and new domains. We were working for car companies. We had to have semantic parsers working for 30 different languages. Well, the only way to do that is not to write a grammar of those languages, but to train it up on something like this. So I certainly believe that. This clunky data manufacturing process actually works, but it gives you better linguistic diversity than you might imagine, but still one might question whether or not they're ecologically valid, and do I not need to collect more and more varied types of utterances. And in particular, you don't end up having dialogues as part of the utterance training. But the critical question for us is, what should the logical forms be? Okay, because I'm going to pass those logical forms to the next part of the system. So when I say go back to the future, I'm saying let's go back and look at the beginnings of dialogue processing. And you'll have to read philosophy to do this, and not just computer science or even linguistics. So Paul Grice in 1957 talked about people's intentions. You don't just want to understand what the utterance means, which was the logical form I gave you, but what does the user mean in using that utterance? What are the user's intentions? In other words, we need to figure out, how do we relate utterances to people's mental states? And we need to infer, what are the reasons behind the utterances? Why did they say that? And ultimately have a dialogue, you can only collaborate. Let's look at an example of collaboration. This is an experiment by Warnke and Tomasello back in 2006.
Phil, I'm sorry to interrupt, but we have some audio issues. Something happened to your microphone right now.
Can you hear me?
It's better now, yes. Thank you.
Okay.
Sorry about that.
All right, let's see if this plays. "18-month-old child."
Phil, I'm sorry again, but we can't see the video actually playing.
Can't see the video. Can you see a video now?
Yes, thank you.
So there's an 18-month-old child. All right, and it just goes on. So what's going on here? Well, this child has somehow learned, either it's innate or has been taught, how to be helpful. In fact, this is an article about chimpanzees who do the same thing. And we're going to submit that being helpful involves being jointly committed to each other's success. So what this kid is doing is it's inferring what the person is trying to do, seeing that there's a problem, and then doing something to overcome that problem. Well, I claim that's what we want to do in collaborative dialogue too. So we want to build systems that are collaborators, that actually assist people in achieving their goals. So that means analyzing the meaning of what you're trying to do, figuring out what actions you're trying to perform. That's a request, that's an inform, etc. And putting them into a planning type system where I can figure out whether your plan's successful. And if it's not, do something to overcome the obstacle that I've detected. So for example, I might say, so where's Dunkirk playing tonight? And you say, the system says it's playing at the Regent Theater at 6 o'clock, but it's sold out. It's also showing at the such and such a theater tomorrow at 7 o'clock. Would you like me to get you tickets to that one? The but it's sold out part means that what I've done is I've done obstacle detection. And that's what that child is taught to do. And that's what we're expecting our assistants to do. And that's what Siri and Alexa and Google Now, et cetera, don't do. Okay, well, plan-based dialogue modeling is something that has a long history in computer science, dating back to the late 70s. In fact, my thesis was on this topic in 78. We worked on this in Toronto with James Allen and Ray Perot. And then a number of other people have been working on it ever since. The whole idea is that the same planning and plan recognition algorithms can be deployed both for physical acts, digital acts, and communicative or speech acts. So if you're planning a physical act, you're reasoning about physical states. If you're planning a communicative act, you're reasoning about mental states. And those two interact, and that's I'll tell you about the architecture we employ. But if you build a system that can reason in this way, collaborative dialogue falls out for free. I don't need to go train up a special dialogue system. What I'm building is a system that's a belief, desire, intention architecture that reasons about our mental states and our speech acts in the course of doing other kinds of actions. And the result is I end up having a dialogue. So the frame-based and slot-filling dialogues that we talked about earlier, where you're filling in values, they fall out for free too, when I'm reasoning about what you know and you need to know in order to perform actions. So let's look briefly at mental states. Now we're going to express this in a modal logic. If you actually want to see the details of the logic, I'll refer to a paper that Hector Levesque and I wrote back in the 90s, which has had a lot of impact since. And we're expressing what the system should do, okay? So you start with a first order base language. I'm assuming you all are familiar with first order logic. Predicates, functions, quantifiers, negations, typed variables, modal operators. And the modal operators are belief and knowledge and goals and intention. So you might say an agent believes something where P is a proposition. And a lot of people have talked, infinitely about that. But the important point of this is when you're reasoning about beliefs, you're reasoning about what people believe and know, but it's vague. I might say, John knows Mary's phone number, but John doesn't know what it is. I mean, John knows Mary's phone number, but I don't know what it is. But because I think John knows it, I can ask him, what's Mary's phone number? So how do I represent that? I can't represent that with a database because I won't know what to put in the database. I can't put in a number because otherwise I would know what it is. And I can't put in just a quantified, existentially quantified variable because then it just thinks Mary has a phone number, not that he knows what it is. So we use this expression, John knows the referent of a variable with a type separated by this pound sign. There exists something of that type such that John believes that P is true of it, okay? Where P is the phone number. You'll see a lot of that as we go along. And John knows whether or not it's raining. Well, I can ask John, is it raining? But that's different from John believes that it's raining or it's not raining, which is a tautology. In neither case can you use a standard database for this. Likewise, in goals and intentions, that's what that paper was about. We talked about a persistent goal, which is a goal that you keep at least until you have to drop it. And we can talk about that at length. And an intention is a persistent goal to do an action. Now, you could build, using this logic, you can build an operational semantics, which is supposed to behave according to this logic. It's a belief, desire, intention architecture, in which you observe the world that influences your beliefs, that influences your goals, which causes you to find a way to achieve your goals, which are intentions. You might have stacks of those intended actions. When you perform the actions, you discharge the goals. It's a lot more complicated because you might fail, etc. So how do you represent actions? Well, it'll be sufficient for the moment to represent them in strips-like operators. If you're familiar with the beginnings of artificial intelligence, look up strips. Basically, actions have names. Here are the slots, the roles, the parameters, and their types. They have preconditions, formulas that have to be true for you to perform the action. They have constraints on the parameter values. They have applicability conditions, formulas that must be true but can't be made true. For instance, tickets have to actually be available. And they have ways to perform these actions. They're hierarchical decompositions. And then after you're done performing the action, certain effects hold. Now, I won't read this to you, but let's just say everything I'm showing you now has an internal representation. Here's a representation for servicing an automobile. Here's the English. Servicing an auto or a repair shop services an auto on a certain date at time. The constraint is the repair shop is located at a particular location. The precondition is, by the way, I'm using prologue-like notations where capital letters mean variables. The precondition is a user has an appointment and the auto is located there at the appropriate time, and the effect is the automobile is fixed. Okay, so you can imagine having huge quantities of those for your back end, you know, all of the skills in Alexa. But you then have communicative actions, informing, offering, requesting, suggesting, confirming, informing that the value of a description, informing whether or not something is true, or WH questions or yes, no questions. So I can reason about these as long as I can reason about the mental states using the same planning operators. So a WH question, well, here's the logic, here's the English. The speaker asks a WH question to a listener about the referent of a variable such that a predicate holds, and that hat means such that. So the precondition is the listener knows the referent of that description, Mary's phone number, and the effect after the WH question has been executed, then the speaker knows the referent of the description. Now it's actually more complicated than that because this is a macro operator, but that's enough for now. Okay, so in planning, many ways to do planning. There's strips planning, there's hierarchical planning. Essentially think about backward chaining for the moment. From an effect, you figure out what action, if you want an effect, you figure out what action will achieve that effect, and you put that action in the plan, and then from the action, you put the precondition in the plan if it's not already true, and then you expand the action into its body, and that becomes hierarchical planning. But the critical thing for us is that in order to perform an action, you have to know what the obligatory arguments are. In other words, you need to know what the reference of the slot values are, subject to the descriptions that are in the, or to the constraints that are in the action definitions. And if you want to achieve P, you need to know whether or not P is true, because if it's already true, you won't bother. Plan recognition is involved going the other way. If I start with I have a certain condition that I think you're trying to achieve, then maybe if it's the precondition of an action, then you're trying to achieve that action. And if I see you trying to achieve an action, then you're probably trying to achieve the effect. And one of the effects that we find people doing is the normal activity. People want to go places, for instance, to do the normal things that you do there. And there have been many different ways of doing plan recognition. So for example, a slot filling question, what time do you want to watch a particular movie? The user is asking a WH question. The precondition is the user knows the referent of the time the user wants to watch the movie. And the effect is the speaker knows the referent of the time the user wants to watch the movie. So there's your slot, the time the user wants to watch Rogue One. Okay, notice it's got the user wants in the middle of that. So the dialogue, and these are modal operators, the dialogue occurs when this question is constructed from the action definitions, namely the definition of watching, via that no value inference that I told you before, which says in order to do an action, you need to know the values of the arguments. Okay, and going the other way, a common pattern of plan inference is, for instance, if the user wants to know a location, the user is going to want to go to, may want to go to that location. In order to go someplace, you need to know the location, so you need to know the route to get to that location. The user may want to do the normal activities you do at that location, and so the precondition of that normal activity has to hold. And then the reason you do that is to achieve the effects of the normal activity. So, in other words, two examples, if you want to go to a movie theater, then you may want to watch the movie, meaning you have to have a ticket, and then you will have seen the movie. Or if you want to go to a gas station, then you may want to buy gas. The system has to have it, and then you have it. All right, so I'm going to give you a few minutes of a system we built along to these principles. And you'll understand and realize it's reasoning through those formulas that I gave you. And it's doing this in first principles. This is going back to basics.
Hi, I'm Phil Cohen.
Sorry for the intro.
Today I'm going to show you a prototype collaborative plan-based
Can you
dialogue
hear?
manager that reasons about the user's beliefs, desires, and intentions. It doesn't just answer questions or perform actions, but tries to infer why you asked them. That is, what was your plan? And do something to enable your plans to succeed. So let's begin. Let's start with a simple question. Where is Arrival playing? And here the system answers the simple question by saying it's showing at 1900 at the Roxy. I recommend you watch it there. And I recommend you take the following route to that location. Well, you might wonder, why does it ask and why does it answer your simple question by recommending a route? And that's because it is inferred that you don't merely want to know the answer, but you actually want to go to that theater, so you need to know the route. Now, if I continue, the system says, would you like me to purchase tickets to Arrival for you? So the system has not merely reasoned that you want to go to the theater, but you actually want to watch the movie in order to have seen the movie. And you're going to need to have tickets. And it wants somebody to purchase tickets for you. So it decides to be proactive and asks you whether or not you would like it to purchase tickets. And then you could go on to say yes. Now, the system has inferred not just the answer to the question, it has inferred the plan that that question is embedded in. That is, you want to know where it's playing in order to go there, in order to watch it, in order to have seen it. And you need some information, which is where it's playing, and you need to have some other data, namely the ticket. So that's why it offers to purchase the ticket for you. Now let's see what happens if things go wrong. Where is Dunkirk playing? So again, the system tells you where it's playing. The movie theater that's showing Dunkirk at 16:30 is the AMC 10. It tells you what you need to know, not simply the answer to the question. It knows you need to know the time as well, because it's reasoning that you actually want to go to that movie theater, and it's telling you how to get there. But instead of recommending that you watch it, it says, I'm very sorry, there are no tickets available for Dunkirk. So what else does it do? It finds another way for you to achieve your higher level goal, which is to have seen the movie. So if we look again at the goals the system has, it's reasoning that you want to know the route, you want to know the movie theater that you want to go to, that you want to take, you want to know the time, you want to know the place. So I want you to know all these things because I'm going to collaborate with you. And that's what motivates the system to tell you the information that it does. And then it checks the preconditions on the plan, and it finds that you can't watch the movie at the movie theater. So it creates a new goal, which is to watch the movie on TV, because that achieves your higher level goal of having seen the movie. So what it has done is it's apologized to you, it's told you where it's playing, it's recommended you watch it on TV. And that you take a certain route. So here the system is reasoning about the purpose behind your question, not simply answering your question.
Okay. Now, one thing about a system like this, it's inherently explainable. If you look at some of the chatbots, you ask it, why did you say that? You're going to get nothing. Likewise, if you asked one of these task-oriented dialogue systems. But behind every utterance here is a plan. So when you say, where's Arrival playing? The movie theater is showing it as the Roxy. Would you like me to purchase tickets? Why did you say that? The system can, in principle, tell you, the reason I offered to purchase tickets for you is because I think you need tickets to the movie and I know how to purchase them. Now, you might have, that's a pretty obvious response, but you can't even get that response from any systems that you see right now because they're not reasoning about why they did. So in summary, semantic parsing and dialogue management is what I'm suggesting we want to break things up into. And I believe you're going to want to build a general BDI architecture and a belief, desire, intention architecture, and then your dialogues will actually have a rational basis. But I want to say one other thing. I want you to consider the ethics of dialogue systems. So imagine in a few years, and it won't be long, before you have capable dialogue systems that are built with deep fake voices, like your family members, and human likenesses, which I can do with any few photographs of a person. And we train them up in boiler rooms with scammers. So they're watching how people the scammers are interacting with people, and they're getting good at this. And they communicate with you by video or voice calls. They can prey on seniors, children, disabled, ordinary adults, and people wouldn't be able to detect it because it's using your loved one's voices and your loved one's faces. So these systems could scam people at scale, okay? Millions of people to send money, open doors, track you through, find your social security numbers, etc. How are you going to defend against this? Well, one thing I'm going to suggest is the plan-based dialogue systems actually have a built-in defense mechanism. Because what happens is the first thing you do is you infer the user's plans and intentions. So if you can build a good system like this, what the system is doing is trying to infer what the speaker is trying to get me to believe or intend or do. So the trying to get me to believe protects my own mental states. I don't just decide to believe or intend or do what it is you say. Okay? And I could decide to believe you or collaborate or not based on the identity of the speaker, system's obligations and permissions, which is something none of these systems actually reason about. So the system could engage people in dialogues to find out whether or not you know the magic words, whether you know my mother's birth date, etc. So finding ways to interact with people to just be skeptical. You're going to build a skeptical dialogue system. That's my defense before you actually get to talk to me. Bonnie Dorr at IHMC has been working on similar topics. So you can imagine there's going to be an arms race between building defensive dialogue systems and systems that are trained up in boiler rooms. And I think we really need to consider how to protect users from better dialogue systems, from malevolent dialogue systems. Okay, so the conclusions. I believe that our poor dialogue management of today is a limitation to having useful assistants. As a lot of people have noted, Alexa is typically used for setting timers and a few other simple things, but it's not really used to its full intended capabilities. And one reason why is having good dialogues. And of course, they're working on it, but I think you might need a different approach. In particular, the approach I advocate is going to reason about why you said what you did and to plan a collaborative response. But it needs to be able to represent a variety of mental states that are not trivial. But if you do so, your dialogue system can be independent of the domain. I don't have to keep training it up to learn how to talk in different domains all the time. but we'll need to improve our reasoning capabilities and representational capabilities rather than in the chatbot's role approach, which is to avoid all reasoning and representation. And I think that's throwing out the baby with the bathwater here. And of course, you're going to have to reason about uncertainty. I believe you want me, want to know something, or I believe that you know something. Well, I believe that you likely know something, and I'm going to operate on that basis. There are a couple of papers I can refer you to that elaborate on this at length. And there are a million papers that are in the background that that you can see in the video. Okay, done.
Thank you very much. The audience is raving. You can't see them right now, but they're all clapping. Thanks very much, Phil. Great talk. We have time for a few questions. And folks, if you can put your questions into either the Hoover app or just the Q&A here on Zoom as well, that would be great. The first question was asked by Rishi Rai Atikari, and I apologize for butchering your name. And there's, can we gauge opinion of people from their speech? And how different are opinions from sentiments, and how do we approach in differentiating between the two? So the question is about, not sentiment, but actually opinion. And I think it's in times like these, that's a really, really relevant question.
I think you might be able to use prosody. So certainly there are people doing multimodal work on deception detection, looking at micro movements of faces and prosody to determine whether or not you're being deceptive, and doing so better than classical lie detection. So that's an example of, quote, an opinion. But I do think you can use prosody as to finding out, to determine whether or not people are confident in what they're saying or not. And presumably, if you're speaking a fact, you might be confident. But, there are some people, they shall go unsaid in this venue, who are very capable of lying with a very straight face. And having multiple lies in the same utterance. So I think systems are capable of doing this and can be made capable of doing this. I'm sure Facebook is trying to do exactly that. But it's, as the example of "this is the best meal I ever ate," the ironic utterances. I want to find out whether or not you're believing what you're saying, or being sarcastic or joking or what have you. So I think those will require a much better analysis of prosody and pitch accent and things of that sort than we're currently deploying in ASR systems right now. ASR systems, except the research systems, but the deployed systems generally are ignoring prosody. And we could do a much better job of that. Next question.
So I was kind of like asking you a similar question about sarcasm, and you mentioned that. One of the issues with relying only to written language, like transcriptions, like in social media and all that, is that there's this important modality that is not there anymore. Just from personal experience, I lived in England for a while, and I tried to understand the English and the sarcasm, and I think I failed utterly. Even having all kind of modalities and then analyzing the prosody. There's like 5 million ways of saying great in a sarcastic manner. So I think that's a serious challenge in here. And there's another question here. Do people have, asked by Dan Scarafoni, do people have different fluency when talking to a machine rather than a human? Do people speak in the same way? If not, is the domain adaptation difficult? So do people talk differently to machines than they talk to humans?
They absolutely do. Okay. And that's based on the expectations of what you think your recipient can do. So that's a moving target. What I mentioned with regard to complex utterances, well, people don't give complex utterances to machines. because they don't think they can handle them. Now, what you find, especially there's a difference in typed language and spoken language, is that people will rely more on dialogue and than they do in spoken language with people than they do if they're typing. You'll find that people break things up into a finer grain using prosody to confirm. So you'll have much finer grained interactions when you're talking to people than when you're typing, and especially if you're talking to computers. And computers, people tend to think I have to create more full sentences. So there's been a lot of work on that topic, and I can't, relate all of it. But yes, they do talk differently. So you got to make sure you're, and that's one of the reasons why the current systems fail, is because they are not really collecting data with real people. They're generating data with a user simulator. Okay, and a reason to do Wizard of Oz systems, that is, there's a person behind the scenes whom you don't know as a computer or as a person, is because then you'll get different expectations and you'll interact differently, provided your wizard is responding in a way that is fast enough and has the appropriate kinds of errors. So you can make it a person try to emulate being a system, so that you can collect data about talking to systems that don't exist yet. And some of that involves how fast, if you see a Wizard of Oz system somebody's doing, the first question you ought to ask is, what's the response time? If the response time is a person sitting there typing in a question to some other system, and the response time could be 10, 20, 30 seconds, that blows the whole cover as to what kind of system it is you're dealing with. When we did Wizard of Oz systems back in the 80s and 90s, we hired fighter pilots to be wizards so that they could respond really quickly. And we were getting response times less than a second. And that's basically what you're going to need to maintain the illusion that you're talking to a person or a system, depending what it is you're trying to emulate. Okay, next question.
George Boateng asks, in the system you propose, how do you address the fact that the system's assumptions of the user's intentions could be wrong? Interesting question. I had a similar one.
Yeah, well, you're going to need to reason, and I didn't go through that, with, you'll need to train up some certain probabilistic analyses, but, and as below a certain threshold, you might question as to whether or not, as you say, would you like me to purchase tickets for you? Or you're just, because one of the alternatives is that my plan doesn't extend any further than this. Okay, and you're inferring further higher level plans. So you're going to need to look for confirming evidence. You also may be given, instructions by the users that, never do this kind of, an inference. But of course, we expect people, people are constantly doing this. If you don't anticipate what people are trying to do and you respond literally all the time, you will be thrown out of your community, whatever that is, your family or some other social gathering. So we're expecting you to do this, and you better be good at it. And that's what makes for a community. We have certain expectations as to what's normal behavior in that community. So systems are going to have to learn to be pretty good, very good at this. You can learn to confirm, but these confirmations could drive everybody bananas if you don't actually learn from them and actually get good at it. Okay.
Great. Next question from Flora Selim. How far are we from having systems that could sustain extended dialogues? Sorry, Flora, to just jump in here. I had a similar question because the interactions you presented and the interactions we have with Alexa and Sirius and the like, they're relatively short, right? There's like individual statements. You ask Alexa to set the timer, Alexa does it, move on. That's not like an extended dialogue we would have between humans. And her question, my question as well. So how deep in these dialogues can we go at the moment? And then she continues, and how far is it from a system that passes the Turing test on complex tasks, such as in debating, arguing, convincing someone, etc.?
All right, well, those are two very, I've been looking at transactional dialogues rather than Turing tests. But in transactional dialogues, that particular system is capable of, doing significant slot filling dialogues. It can also reason about, if you said, what time you want to eat, and you say, I don't know, but Mary does, it'll go off and plan a question to Mary. Okay. It could also go off and plan questions to the back end. Call up the service provider and have a conversation that way. And Google Duplex is doing something like that. And of course, they have all the resources in the world. But it remains to be seen how general that is. And so I think you're probably going to see 5 to 10 years once people understand how to do this properly, for more complex dialogues of the kinds that we would anticipate, say, in the old days when you had a travel agent, okay? And you provide the constraints that are necessary to for your trip. Those constraints are not going to be just simple, simple one-offs, and you can start emulating this here as I want a dinner in a movie, okay? And try that with these systems and try to figure out how to coordinate the dinner and the movie in various parts of town, assuming, it's not COVID times. How long it takes to get from place A to place B, whether, if I go to the movie at this time, can I get there in time if I have dinner, a reservation at this other time? So I think what we are going to need to do to have more complex dialogues in a transactional case is do more studying of constrained interaction, constraint-based interaction. Because what happens in life is our constraints are violated all the time. And when things fail is when actually the dialogues get interesting. So as I say, I'm not going to talk about the Turing test. I'm just going to try to build useful systems, but certainly ones that can handle more complex constraints. Okay.
Excellent. Thanks very much, Phil. We are a little bit over time. Maybe we have time for one more question, and everyone else, apologies. I believe there's a gathering in Gathertown where Phil, if he has time, can hopefully answer a few more questions. Final question from our online chair, from Alex Marakakis. He says, video conferencing like Zoom limits some of the visual cues we have, obviously, and forces us to rely on audio and speech a bit more. Do you see any opportunities in that? I mean, this whole disaster we are living through right now is one thing, but one could also argue there might be an opportunity in that. I think that's what he's alluding to. And he gives you bonus points for thoughts on virtual conference presentations.
Well, some of the video cues that we don't get in Zoom, for instance, each of you is very small. And the more people there are, the smaller you get. So one of the things you don't get are the micro facial movement. And the microfacial movements are the ones that have been found to be critical to figuring out the veracity of the speaker. Okay, so when I said people are doing multimodal deception detection now, well, they're using beautiful images of people's faces. The more you diminish that resolution and the time lags, the less capable we are of deciding whether or not the person is speaking the truth. So it's it's a shame, but that's just sort of life in the pandemic. On the other hand, you know, before most of your time, there was this debate between Richard Nixon and John Kennedy. Okay? And it was the first televised debate on, you know, in the presidential election. And if you listened to the debate, you thought Nixon won. And if you watched the debate and you saw Nixon sweating and had a very dark 5 o'clock shadow, you got a very different impression of Richard Nixon, probably the true impression of Richard Nixon. And those people thought Kennedy won. So these cues are really important. And we are just at the beginning of understanding, at least at a computational perspective, which cues are most important. Prosody, we need to do a lot more work on, and facial body gestures, etc. We also need to do a lot more work on. So multimodal interaction is going to be critical for that in the future.